Welcome to part 2 of my video series on the versatile shield for prototyping and implementation of Arduino Nano projects. In part 1 I gave you an introduction on the functionality of the shield. The main feature is its versatility. On the one hand it can be used for efficient and rapid prototyping, and on the other hand it can be used as a base for a device. In detail I walked you through the functionality of the printed circuit board by explaining you the scope of its circuitry. The functionality of the circuits is a good point to start with for a variety of projects. In the meantime I reworked the base code and the hardware design files. You can find these files for download now in the description of this video and the other videos which are related to this video series. I used the free software Fritzing to design my PCB. If you want to use the design file for your purposes, you need to install this software. In part 2 of this video series, I want to detail the design considerations behind the hardware. I won't give you an introduction on basic Arduino tasks. The focus of this video is restricted to the hardware design considerations behind this shield. This also includes to put some mathematics behind the shield. For this reason you should have some basic knowledge to follow this video. On the one hand you should have some knowledge on electronics, in detail Ohm's law, the computation of power and the behavior of resistors in series. And on the other hand you should have basic Arduino knowledge on how to control a button, control an LED, control a Piezzo buzzer and how you can use voltage dividers with an Arduino to measure voltages. I will outline the hardware design considerations in detail by using the hardware design view of the shield. On the hardware design view picture you see here, the copper shield is removed for a better view. Furthermore, the picture you see is a picture of version 1.1 of the shield, which includes some improvements. For each circuit part I will walk you through the hardware design considerations in detail. For the design of the shield I used the free software Fritzing. In this software you can start your design with a reality-like sketch. On the depicted picture you see the sketch of the shield. At a first glance it looks more complicated than it is in the end. I will extract each functionality group and put it on a separate slide for the explanation of the hardware design considerations behind it and to explain potential mathematics to dimension the assembly parts. Let's start with the leftmost circuit part. What you see on the sketch are some female header pairs. One side of the pair is connected to the 5V line and the other side of the pair is connected to the ground. On the PCB view you find these pairs here. You can use these header pairs to supply a custom element on the custom area with 5V. Okay, that's it about the 5V pairs already. Let's go on to the next circuit part. The next circuit part is an L7805 voltage conversion circuit. This circuit is a bit more complex. You can use this circuit if you don't want to use the internal voltage conversion circuit of the Arduino board. The main reasons are saving the Arduino board from heating up and using voltages higher than the recommended maximum voltage of the Arduino board, which is 12 volts. The least input voltage of the L7805 conversion unit is 8 volts or higher. To attach an external power unit, the sketch provides two pins which you can find here in the hardware design view. Furthermore, there is a power on-off switch in the sketch, which you can find here in the hardware design view. To prevent exhausting the external power source if it is a battery, there is a pin in the sketch to measure the voltage. In the hardware design view you find this pin here, directly next to a voltage divider pin. If you solder male headers to both pins, you can connect them with a jumper. To dampen voltage peaks in the circuit, there are two capacitors. These capacitors are both of 10 microfarads size. You can find one capacitor on the inside of the circuit and the other one on the outside of the circuit. To prevent high frequency oscillations, there is a ceramic capacitor of 100 nanofarads on the 5V outside. The sizing of these capacitors is how it worked fine for my projects. When you consult the internet, you find a lot of other different options. In detail I can't explain you what is best for which application. When you intend to use an L7805 voltage conversion unit for your project, then you should attach a heatsink to it. Let's have a look at the following example. If you have an input current of 200 mA at a voltage of around about 12 volts, then there is a difference voltage of 7 volts that need to be consumed somehow. This consumption is done by producing heat. So what is the heat in this case? The power that needs to be dissipated by heat is the voltage multiplied with the current. In this example it's 7 volts multiplied with 200 milliamps. So it's 3.5 watts, which need to be dissipated on the tiny size of the L7805 voltage conversion unit. Have you ever touched an old-fashioned 20 watts bulb? If yes, you can imagine how hot it gets. Okay, let's go on with the potentially most complicated part of the circuit from a mathematical point of view. It's about the voltage dividers for voltage measurement. There are 2 voltage divider circuits on the breadboard. Each has a pin for voltage pickoff. In the hardware design view you find these pins here. Furthermore, each voltage divider consists of 2 resistors, which divide the voltage. In between the resistors are Arduino pins A0 and A1 to pick off the voltage over one of these resistors. The voltage range is 0 to 5 volts. Internally in the Arduino board it is translated with 10 bits accuracy. That means that the 0 to 5 volts are translated to 0 to 1023. In the hardware design view you find the 2 resistors here and here. Let's go through an example. Let's assume your device is powered by a 3S LiPo battery which has a maximum voltage of 12.6 volts if it is fully charged. This voltage is distributed over 2 resistors. One of the 2 resistors has 4.7 kilo-ohms and the other has 1 kilo-ohm. The voltage over the 1 kilo-ohm resistor is measured by an Arduino analog pin. So what is the measured value in our example? If you put in 12.6 volts into the following equation together with the resistor values of 4.7 kilo-ohms and 1 kilo-ohm, then the resulting value is 2.21 volts. Internally in the Arduino this is of course a value somewhere in between 0 and 1023. If you're going the other way around from 2.21 volts back to the battery voltage, you're of course getting 12.6 volts. Look at this equation and put in the values to calculate it. If the battery voltage goes down in current consumption to 11 volts, then the internally measured voltage would be 1.93 volts. When you are using voltage dividers, it is very important to put in the exact resistor values into the equation. Otherwise there can be critical measurement failures. Have a look at the following example. If the real resistor value of our higher resistor is not 4.7 kilo-ohms but 4.69 kilo-ohms, and the real value of the smaller resistor is not 1 kilo-ohm but 0.98 kilo-ohms, then there is a difference of 0.3 volts of the calculated battery voltage. So for the battery voltage calculation, always use the values of the resistors which you have measured with an ohm meter. The next circuit part is pretty easy. The supply of an I2C port is just the supply of a couple of pins. The A4 and A5 pins of the Arduino board can be used as SDA and SCL pins of an I2C port. These are signal data and signal clock pins. Most devices you can attach to an I2C port have a need for a 5 volt voltage. For this reason a 5 volt pin and a ground pin are added to the supplied pins. You find the I2C port in the design view here. The next thing is also simple. It's the supply of a mounting location for LEDs. In combination with this mounting location there is a mounting location for a resistor for each LED. Each LED has a so-called forward voltage, which is the voltage consumption of a specific LED color. For example, for a red LED it's mostly around about 2 volts. Because an LED is a diode, it has an exponential current flow correlated to an increasing voltage. The maximum current flow an LED can sustain is 20 milliamps for a standard LED. So for this reason you need a resistor which limits the current flow to 20 milliamps. The calculation is as follows. You have the 5 volts and you subtract the forward voltage of the LED. Divided by 20 milliamps you get the resistor value. There is a mounting location for up to 4 LEDs. These are connected to Arduino pins D9 to D11, which are PWM pins, and D12, which is a standard on-off pin. The next part of the sketch is the support of up to 4 buttons. In this sketch there is no implementation of a button. It's just the support of 2 female headers, which are in the design view just 2 solder points. To these solder points you can attach each button via wires. For each button there is a location for a pull-down resistor. In my devices I always use 10 kiloohms, but other values are possible. The Arduino pins D5 to D8 are used to support a button. You find the buttons and the solder pins here in the hardware design view. The next thing is the support of a Piezzo buzzer. This is also a very simple circuit. The Piezzo buzzer is just connected to pin D3 of the Arduino board and to a ground pin. The pin D3 is a PWM pin. In the hardware design view you find the mounting location of the Piezzo buzzer here. The next thing is a link up to a breadboard. The link up supports solder pins for 5 volt and for ground connection. You can solder male headers to these solder pins. With these pins you can plug your shield directly into a breadboard, as I showed in the previous video. As soon as the microcontroller is powered with 5 volts, the breadboard is also powered with 5 volts. On the hardware design view you find these pins here. Here you see the 5 volt supply, and here you see the ground connection. Finally, there is a custom implementation area on the shield. This area has no connection to any other parts at all. The custom implementation area is made of triplets of interconnected solder pins, which can be used for any element you want to add to your device. Okay, that's it about the hardware design considerations. In my next video I want to walk you through the base code which controls all these hardware circuits. Thanks for watching, hope to see you in my next video.